All right, I hope my voice is audible. Three people are already watching. Oh my god. So, good evening, everybody. We'll be doing some gate. Yeah, I got up early today. I came back from college early, so we'll be doing an half an hour stream. And then I will go fresh up and then, okay, what's the day? Yeah, day 11. This is day 12, alright. So, right, we will be doing compiler design. Um, we need to know the basics of these. So two grammars are given, Z1 and Z2, and the production rules are given. So we need to understand these production rules first, and then we need to understand what is LL1. Right. Shall we take a screenshot of this question? Yeah. All right. Grammar describes how strings are formed. Okay. Actual symbols of the language, terminals, placeholders, okay, non-terminals. Production rules for expansion means S can produce a string A. Okay. LL1 means scan input left to right, produce leftmost derivation. Decide the rule using only one lookahead symbol. When a parser sees the next input symbol, it must be uniquely choose the production. If two choices start with the same terminal, okay, then the grammar is not LL1. Nice. One string can have two different parse trees. Okay. So ambiguous grammar is not LL1. Unambiguous will automatically be LL1. If E, then S. If E, then S. Else as A. If E, then S. Alright. First understand the language. Both grammars generate A or C. If B, then it's a classic dangling else problem. Look at the productions, okay? First two rules start with F. Yes, if E, then S. And a parser sees if it cannot decide is it short term if then. Okay, this can be attached for. Now, is that the answer? Okay, kind of messed the answer up. Yeah. ChatGPT cannot even do parsing properly. G1 is originally dangling as problem, so it is ambiguous. So we can say that it cannot be LL1. Okay. For G2, if E, then S. If E, then If E, then M, else as 2 passes. Right. No, that is obviously false. All right. Mm-hmm. Mm-hmm. B, then if B, okay, so S maps to if E, then S. If E, then S, else S, and E maps to B. So let's substitute it. E maps to B, so if B, then S is saying if B, then A, else A. Okay. B, if A, then S, if grammar is LR1 if and only if for every non-terminal A, first set of its alternatives are disjoint. If epsilon productions exist, first and follow must be conflict. First set of its alt. Mm-hmm. E plus E and E times E. Got it. So E, right. So for this you can write E is equals to E plus and E. Now again E is defined as E star E, attaching E star E to first E, or you can also do this, right, to second E. So that is alright. So it is the same, right? So if you were to generate a parse ray, if E, let's generate a parse ray both showing ambiguity. So you are writing for F, right? I mean S. If E, then S. If E, then S. Again, All right. All right. Yeah. If E then S, that is a derivation, and again you can derive E as if E then M else S. Okay. And S is defined as M. Alright. Okay, if E then S. Yeah, that got it. M. And if E then M else is okay. Or C or B. Okay, that is correct. And if E then S, right, if E then S and C. Alright. We need some theory before solving this question. Backpatching in a compiler for intermediate code generation. Backpatching can be used to generate code for Boolean expressions in one pass. Backpatching can be used to generate code for flow of control statements in one pass. So you need to know what backpatching is. Let's see. Compiler design. Control flow constructs loops and condition statements using intermediate code generation. Leaving field of an instruction blank initially for forward reference later. Boolean expressions are statements whose results can either be true or false. So let's see. I just opened this one, right? Yeah. I just opened this one. Let's see the explanation. Okay, that is a direct question. If you know the theory, you can solve that. Okay, we don't know what is attributed and unattributed or. I guess we should leave comparator design. We should not touch it until we actually read some theory. So we know some amount of everything except this one, right? So why wasting time on this? We will read some theory and after that we will come to it. We should be able to at least comprehend these questions. So logical address 2 power 32 bytes, 2 level hierarchical paging 4096 bytes. Okay. A logical address is divided into B bit index to the outer page index, an offset within the page and an inner page table and the offset within the desired page. Each entry of an inner page table uses 8 bytes. All the pages in the system have the same size. The value of B is. So 2 power 32. So that is a 32-bit addressing system and 2-level hierarchical paging. 2-level hierarchical paging. We need to know that one. Page size is 4096, that is basically 2 power 12. So that 12 bits will be occupied for the page size and logical address is divided into B bit index and an offset within the inner page table and an offset within the desired page. Each entry is 8 bytes. So offset is log 8, that is 3 bytes of offset. So you got 20 physical addresses. Out of that, 3 takes 6 and okay. Let's see. Outer page table index, inner page table index, page offset. Alright. We kind of did that correct. Page size is 2 power 12. So page table entry size 2 kilobytes. 2-level hierarchical paging. Alright. We actually need a little more understanding of this question. Let's see. How many bits a 32-bit logical address are used to index the outer page table? Nice. How many bits used to page the outer page table? Anything else in this question exists only to force constraints on all 32 bits, on how all 32 bits are split. Nice. Okay. That is non-negotiable. Okay. Page size. The last 12 bits of any logical address are used to select a byte inside a page. So page size is 2 power 12 bytes. So last 12 bits to select byte of page. Okay. Nice. That is offset. That is offset. 20 bits left. Alright. Two level hierarchical paging. Instead of one big page table, we have outer page table and inner page table. Okay. A page table cannot be stored in memory just like any other data. A page table itself must fit inside pages. All pages in the system have same size. So programs think memory is okay. Physical RAM is finite, fragmented, shared by many programs, constantly changing. So OS must answer the question. A program asks for address X, where is that actually stored in RAM? Virtual memory. Okay. Program name combined. The logical address does not. Each process has its own page table. CPU has a special register, page table base register. Page number offset. Okay. Okay, that makes sense. So instead of this one table, we have page is a small fixed chunk of memory. Memory allocation happens in pages. Protection happens per page. So anything stored in paging in number of pages. Whole number of pages. All page tables are same size. This is not decorative text. This sentence exists for one reason only. Code pages, data pages, stack pages. Wait. Page tables all are allocated in page-sized chunks. And another page table is a table of entries. Okay. So 32-bit, you understood the total length, and page size offset is 12, you understood that one, and this length is 20. Okay. So from that, um, entry is 8 bytes. All pages same size. Okay, and so page table is equals to one page, but we know one page is 2 power 12 and the entry size is 2 power 3. So number of entries is equals to 8. So 8 bit for inner address, and this is 9. So 9 bits and 11 bits. That is good. That is good. Oh, we are stuck with the same. We are stuck in the same question, but still, this lag is important. Yeah, I have done this one. 0, 1 to 8 milliseconds. Okay. Execution time. Shortest remaining time first algorithm is used in CPU scheduling. Ignore context switches. Average turnaround time of 4 processes. So at time 0, the process P1 arrives, and at time 2, process 2 arrives. At time 1, process 2 arrives. At the time 2, process 3 arrives, and at time 8 something, the process 4 arrives. Okay. Here the execution times, let's also write them. 10, 13, 6, and 9. Shortest remaining time first. Uh-huh. So how does the execution actually happen? So let's see. It is preemptive. SRTF is preemptive. So that means it can make a context switch without actually needed to complete the process. Like even if the process does not complete, you can what do you say? You can switch that to another process. Okay. At time 1, P2 arrives. Okay. By this time, P1 has 9 milliseconds since 1 millisecond is executed. So it will continue. At T2, P3 arrives. So by this time, P1 will have, you see, 10 minus 2, that is 8. And P2 still has 13. But P3 needs 6 milliseconds. Okay, so from 2 to 8. Uh-huh. Okay, P1 is with 8, P2 is not touched yet, and P4 is with 9, so shortest is 8. Nice. After P1 finishes, you got these two. Which one? The 13 and 9 one. You will run the 9 one, 17 milliseconds. Okay. Nice, right? So let's do a line at 0. P1 arrives, and at 1, P2 arrives, and with 10, with 13. By this time, P1 has 9 remaining, and at 2, P3 with 6 arrives. By this time, P2 still has 13. P1 has how much? 10 minus 2, that is 8. So what will it pick out of this? It will pick P3. So for 6 seconds it will execute it. P3 executing, P1 executing, P1 executing. And at 8 second, P4 with 9 joins the chat, and this is done. P3 is done. Now P2 with 13 and P1 with 8. So we got 8 1, 8 plus 8 at 16 seconds. Right. P1 is done. And now what you got, P4 with 9 and P2 with 13. P4 will be done. Alright, so P3 is done at 8 seconds and P1 is done at 16 seconds and P4 will be done at 16 plus 9. How much? 25 seconds. At 25, P4 or P3 remains and P4 will be done. Now you got just P3. 25 plus 13 is 38. So P3 takes 38 seconds. So you just need to calculate average of all of these. 24, 49, 49 and 38. 1787 by 4. That's it. 21. There will be 3. 330. So 4, 6, 4 7s are 28. That's it. What? No. What? Okay, turnaround, completion, minus arrival. Yeah, that is true. The kind of like extra time wait. So P1 started at 0. So P1 will be same and P3 kind of enters the chat at 2. So it will be 6 and P4 enters the chat at 16 and 16, right, that is 9 itself and P3 kind of entered at 2, that is 36. So 36 plus 9 is 45 and 16 plus 6 is 22. So that is 767 by 4, right, that is 1 and 4 6 are 24, 3, 4 7 are 28, 2, 16, wait, what? 16 plus 6 plus 17. Okay. P2 entered at 1 second, so that is 37, okay. And P4, that is 9. P3 is 6, okay. Turnaround is 16, okay. Okay, when did P4 arrive, dude? P4 arrived here only, as you can see. That is 17, yeah. You kind of messed up. You need to calculate the turnaround time there and then. Yeah, but I got the spirit anyways. So how many questions did you do? That's just 2. This is set to a demand paging with 3 frames. In the following page references the contents of the frame as followed initially, and after each reference from left to right, the marker reference cause page replacements. Which one of the following could be the page replacement policies? Wow. 1 2 3 4 5 4 1 6 4 5 1 3 2. The contents of the frame are as follows initially. So initially the contents are 0. Wow, dude. Everybody's saying that. Okay. So this is the data. I see. So these are the frames. Okay, one is inserted, and two is not there. So obviously, two is inserted. That causes a what do you call cause page replacement. Okay, three is inserted, and all right. So to insert four, four is not found. So if it is LRU, least recently used. The least recently used one is 1, so 1 should be replaced, that is true. But 2 is replaced. Okay. Least frequently used. We cannot decide that. Most frequently used. We cannot decide that one as well. Alright, so 5 is not there. So 3 is selected. I don't know why. So okay, 4 is there, 1 is there, and 6 is selected from 1. Yeah, so the thing is, 4 is replaced in the middle, 5 is replaced here. Right, let's do this. One guy told FIFO 1, 2, 3, and 4 is replaced. So LR would have done like this. Okay, least result. Nice. Least recently was until that point. An active process in operating system. Single instances of distinct types of resources. The resource allocation graph claims the edges. So R1, P1, R2, P2, R3. Resource R1 is assigned to process P1. So claim edges. P1 process is okay. How to draw the resource allocation graph? I wanted to do this question. How to draw the resource allocation graph? Process request for resource. An instance is allocated. An instance of resource is allocated. Okay. All right. So this is assignment and this is claimed. So we need to, I don't know how to draw the resource allocation graph. And then what? P1 the assignment is okay. Resource R1 is assigned to process and so process 1 is waiting for resource 2. Process 2 is waiting for resource 3 and process 3 is waiting for resource. Wait, P1 R2, P2 R3, P3 R1, P4 R2. So how is it deadlocking? We first need to analyze what causes the deadlock. If you abort process P1, then P3 will obviously get R1. And if P3 got R1, do you need to abort both of them? No, if you kind of abort this one, right? Let's say process 1 and it won't request for it anymore. And R1 you can allocate to P3. Nice. And there is no deadlock. So why am I feeling like A should be one of the answers? So I drew it, man. I drew it. So that is how you draw a resource allocation graph. Um, sure, bro. Yeah, I guess there is a problem with the mic and all. I'm talking in normal sound as I always do. Initial system was deadlock. Okay, aborting P1 will make the. So that is what we got. R2 for P2, P4 for R2, P2 for R3, and after P3 finishes. So P3 would finish its execution by holding R1 as it is free now, but there still would be deadlock due to cycle R2 P2. Okay, R4 P4 R2. Okay, okay. Okay, so deadlock detection you can use here. You can do it using Banker's algorithm. I see. So aborting P3 is still deadlock. Three and four, okay. Got it. So we'll continue from then and bye.